In communications and electronic engineering, a transmission line is a specialized cable or other structure designed to carry alternating current of radio frequency, that is, currents with a frequency high enough that their wave nature must be taken into account. Transmission lines are used for purposes such as connecting radio transmitters and receivers with their antennas, distributing cable television signals, trunk lines, routing calls between telephone switching centers, computer network connections, and high-speed computer data buses. This article covers two-conductor transmission lines such as parallel line, coaxial cable, stripline, and microstrip. Some sources also refer to waveguide, dielectric waveguide, and even optical fiber as transmission line. However, these lines require different analytical techniques and so are not covered by this article. See Waveguide Overview. Ordinary electrical cables suffice to carry low-frequency alternating current, such as mains power, which reverses direction 100 to 120 times per second, and audio signals. However, they cannot be used to carry currents in the radio frequency range or higher, which reverse direction millions to billions of times per second, because the energy tends to radiate off the cable as radio waves, causing power losses. Radio frequency currents also tend to reflect from discontinuities in the cable such as connectors and joints, and travel back down the cable toward the source. These reflections act as bottlenecks, preventing the signal power from reaching the destination. Transmission lines use specialized construction and impedance matching to carry electromagnetic signals with minimal reflections and power losses. The distinguishing feature of most transmission lines is that they have uniform cross-sectional dimensions along their length, giving them a uniform impedance, called the characteristic impedance, to prevent reflections. Types of transmission line include parallel line, coaxial cable, stripline, and microstrip. The higher the frequency of electromagnetic waves moving through a given cable or medium, the shorter the wavelength of the waves. Transmission lines become necessary when the length of the cable is longer than a significant fraction of the transmitted frequency's wavelength. At microwave frequencies and above, power losses in transmission lines become excessive, and waveguides are used instead, which function as pipes to confine and guide the electromagnetic waves. Some sources define waveguides as a type of transmission line, however, this article will not include them. At even higher frequencies, in the terahertz, infrared and light range, waveguides in turn become lossy, and optical methods are used to guide electromagnetic waves. The theory of sound wave propagation is very similar mathematically to that of electromagnetic waves. So techniques from transmission line theory are also used to build structures to conduct acoustic waves, and these are called acoustic transmission lines. History. Mathematical analysis of the behavior of electrical transmission lines grew out of the work of James Clerk Maxwell, Lord Kelvin and Oliver Heaviside. In 1855, Lord Kelvin formulated a diffusion model of the current in a submarine cable. The model correctly predicted the poor performance of the 1858 transatlantic submarine telegraph cable. Applicability. In many electric circuits, the length of the wires connecting the components can for the most part be ignored. That is, the voltage on the wire at a given time can be assumed to be the same at all points. However, when the voltage changes in a time interval comparable to the time it takes for the signal to travel down the wire, the length becomes important and the wire must be treated as a transmission line. Stated another way, the length of the wire is important where the signal includes frequency components with corresponding wavelengths comparable to or less than the length of the wire. A common rule of thumb is that the cable or wire should be treated as a transmission line if the length is greater than 1/10 of the wavelength. At this length, the phase delay and the interference of any reflections on the line become important and can lead to unpredictable behavior in systems which have not been carefully designed using transmission line theory. The four-terminal model. For the purposes of analysis, an electrical transmission line can be modeled as a two-port network, as follows. In the simplest case, the network is assumed to be linear, and the two ports are assumed to be interchangeable. If the transmission line is uniform along its length, then its behavior is largely described by a single parameter called the characteristic impedance, symbol Z0. This is the ratio of the complex voltage of a given wave to the complex current of the same wave at any point on the line. Typical values of Z0 are 50 or 75 ohms for a coaxial cable, about 100 ohms for a twisted pair of wires, and about 300 ohms for a common type of untwisted pair used in radio transmission. When sending power down a transmission line, it is usually desirable that as much power as possible will be absorbed by the load and as little as possible will be reflected back to the source. This can be ensured by making the load impedance equal to Z0, in which case the transmission line is said to be matched. Some of the power that is fed into a transmission line is lost because of its resistance. This effect is called ohmic or resistive loss. At high frequencies, another effect called dielectric loss becomes significant, adding to the losses caused by resistance. Dielectric loss is caused when the insulating material inside the transmission line absorbs energy from the alternating electric field and converts it to heat. The transmission line is modeled with a resistance and inductance in series with a capacitance and conductance in parallel. The resistance and conductance contribute to the loss in a transmission line. The total loss of power in a transmission line is often specified in decibels per meter, and usually depends on the frequency of the signal. The manufacturer often supplies a chart showing the loss in decibel per meter at a range of frequencies. A loss of 3 decibels corresponds approximately to a halving of the power. High-frequency transmission lines can be defined as those designed to carry electromagnetic waves whose wavelengths are shorter than or comparable to the length of the line. Under these conditions, the approximations useful for calculations at lower frequencies are no longer accurate. This often occurs with radio, microwave and optical signals, metal mesh optical filters, and with the signals found in high-speed digital circuits. Telegraphers equations. The Telegraphers equations are a pair of linear differential equations which describe the voltage and current on an electrical transmission line, with distance and time. They were developed by Oliver Heaviside, who created the transmission line model, and are based on Maxwell's equations. The transmission line model represents the transmission line as an infinite series of two-port elementary components, each representing an infinitesimally short segment of the transmission line. The distributed resistance of the conductors is represented by a series resistor. The distributed inductance is represented by a series inductor. The capacitance between the two conductors is represented by a shunt capacitor C. The conductance of the dielectric material separating the two conductors is represented by a shunt resistor between the signal wire and the return wire. The model consists of an infinite series of the elements shown in the figure, and the values of the components are specified per unit length, so the picture of the component can be misleading, and may also be functions of frequency. An alternative notation is to use, and to emphasize that, the values are derivatives with respect to length. These quantities can also be known as the primary line constants to distinguish from the secondary line constants derived from them, these being the propagation constant, attenuation constant and phase constant. The line voltage and the current can be expressed in the frequency domain as when the elements are negligibly small. The transmission line is considered as a lossless structure. In this hypothetical case, the model depends only on the and elements, which greatly simplifies the analysis. For a lossless transmission line, the second-order steady-state Telegraphers equations are. These are wave equations which have plane waves with equal propagation speed in the forward and reverse directions as solutions. The physical significance of this is that electromagnetic waves propagate down transmission lines, and in general, there is a reflected component that interferes with the original signal. These equations are fundamental to transmission line theory. If and are not neglected, the Telegraphers equations become, where gamma is the propagation constant and the characteristic impedance can be expressed as the solutions for n. The constants and must be determined from boundary conditions. For a voltage pulse, starting at and moving in the positive direction, then the transmitted pulse at position can be obtained by computing the Fourier transform of attenuating each frequency component by advancing its phase by and taking the inverse Fourier transform. The real and imaginary parts of can be computed as where at and 2 is the two-parameter arctangent, and for small losses and high frequencies, to first order n and 1 obtained, noting that an advance in phase by is equivalent to a time delay by, can be simply computed as input impedance of transmission line. The characteristic impedance Z0 of a transmission line is the ratio of the amplitude of a single voltage wave to its current wave. Since most transmission lines also have a reflected wave, the characteristic impedance is generally not the impedance that is measured on the line. The impedance measured at a given distance, L, from the load impedance ZL may be expressed as where gamma is the propagation constant and is the voltage reflection coefficient at the load end of the transmission line. Alternatively, the above formula can be rearranged to express the input impedance in terms of the load impedance rather than the load voltage reflection coefficient. Input impedance of lossless transmission line. For a lossless transmission line, the propagation constant is purely imaginary, gamma equals J beta. So the above formulas can be rewritten as where is the wave number. In calculating beta, the wavelength is generally different inside the transmission line to what it would be in free space, and the velocity constant of the material the transmission line is made of needs to be taken into account when doing such a calculation. Special cases of lossless transmission lines. Half wavelength. For the special case where n is an integer, the expression reduces to the load impedance so that for all n, this includes the case when n equals 0, meaning that the length of the transmission line is negligibly small compared to the wavelength. The physical significance of this is that the transmission line can be ignored in either case. Quarter wavelength. For the case where the length of the line is 1/4 wavelength long, or an odd multiple of a quarter wavelength long, the input impedance becomes matched load. Another special case is when the load impedance is equal to the characteristic impedance of the line, in which case the impedance reduces to the characteristic impedance of the line so that for all in all, short. For the case of a shorted load, the input impedance is purely imaginary and a periodic function of position and wavelength. Open. For the case of an opened load, the input impedance is once again imaginary in periodic step transmission line. A step transmission line is used for broad-range impedance matching. It can be considered as multiple transmission line segments connected in series, with the characteristic impedance of each individual element to be Z0, I. The input impedance can be obtained from the successive application of the chain relation where is the wave number of the ith transmission line segment, and Li is the length of this segment, and Z is the front-end impedance that loads the ith segment. Because the characteristic impedance of each transmission line segment Z0, I is often different from that of the input cable Z0, the impedance transformation circle is off-centered along the x-axis of the Smith chart, whose impedance representation is usually normalized against Z0. Practical types. Coaxial cable. Coaxial lines confine virtually all of the electromagnetic wave to the area inside the cable. Coaxial lines can therefore be bent and twisted without negative effects. and they can be strapped to conductive supports without inducing unwanted currents in them. In radio frequency applications up to a few gigahertz, the wave propagates in the transverse electric and magnetic mode only, which means that the electric and magnetic fields are both perpendicular to the direction of propagation. However, at frequencies for which the wavelength is significantly shorter than the circumference of the cable, transverse electric and transverse magnetic waveguide modes can also propagate. When more than one mode can exist, bends and other irregularities in the cable geometry can cause power to be transferred from one mode to another. The most common use for coaxial cables is for television and other signals with bandwidth of multiple megahertz. In the middle 20th century they carried long-distance telephone connections. Microstrip. A microstrip circuit uses a thin flat conductor which is parallel to a ground plane. Microstrip can be made by having a strip of copper on one side of a printed circuit board or ceramic substrate while the other side is a continuous ground plane. The width of the strip, the thickness of the insulating layer and the dielectric constant of the insulating layer determine the characteristic impedance. Microstrip is an open structure whereas coaxial cable is a closed structure. Stripline. A stripline circuit uses a flat strip of metal which is sandwiched between two parallel ground planes. The insulating material of the substrate forms a dielectric. The width of the strip, the thickness of the substrate and the relative permittivity of the substrate determine the characteristic impedance of the strip, which is a transmission line. Balanced lines. A balanced line is a transmission line consisting of two conductors of the same type, and equal impedance to ground and other circuits. There are many formats of balanced lines. Amongst the most common are twisted pair, star quad and twin lead. Twisted pairs are commonly used for terrestrial telephone communications. In such cables, many pairs are grouped together in a single cable, from 2 to several thousand. The format is also used for data network distribution inside buildings, but the cable is more expensive because the transmission line parameters are tightly controlled. Star quad is a four-conductor cable in which all four conductors are twisted together around the cable axis. It is sometimes used for two circuits, such as four-wire telephony and other telecommunications applications. In this configuration each pair uses two non-adjacent conductors. Other times it is used for a single, balanced circuit, such as audio applications and two-wire telephony. In this configuration two non-adjacent conductors are terminated together at both ends of the cable, and the other two conductors are also terminated together. Interference picked up by the cable arrives as a virtually perfect common mode signal, which is easily removed by coupling transformers. Because the conductors are always the same distance from each other, crosstalk is reduced relative to cables with two separate twisted pairs. The combined benefits of twisting, differential signaling, and quadrupole pattern give outstanding noise immunity, especially advantageous for low signal level applications such as long microphone cables, even when installed very close to a power cable. The disadvantage is that star quad, in combining two conductors, typically has double the capacitance of similar two-conductor twisted and shielded audio cable. High capacitance causes increasing distortion and greater loss of high frequencies as distance increases. Twin lead consists of a pair of conductors held apart by a continuous insulator. By holding the conductors a known distance apart, the geometry is fixed and the line characteristics are reliably consistent. It is lower loss than coaxial cable because the wave propagates mostly in air rather than the thin dielectric. However, it is more susceptible to interference. Lecture lines are a form of parallel conductor that can be used at UHF for creating resonance circuits. They are a convenient practical format that fills the gap between lumped components and resonant cavities. Single-wire line unbalanced lines were formerly much used for telegraph transmission, but this form of communication has now fallen into disuse. Cables are similar to twisted pair in that many cores are bundled into the same cable, but only one conductor is provided per circuit and there is no twisting. All the circuits on the same route use a common path for the return current. There is a power transmission version of single-wire earth return in use in many locations.